Hello everyone. Let's continue from moment, curvature, and thrust relationship of inelastic column. And your undergraduate study stress-strain relationship is like this, right? Elastic and plastic. Sigma I, epsilon y, right? So for P equals 0, there is no thrust, no axial force. Then this is the member, moment applied. Then we have, for rectangular section, we have the stress like that. If top and bottom stress is equal to yield stress, at that case, the internal moment equal my, yield moment. Sigma y s. S is section modulus. Section modulus for rectangular section is bh square over 6, right? If the section is fully yielding like this, then we call it the MP. The internal moment is MP, right? So MP equal sigma y g. G is plastic section modulus, right? For rectangular section, plastic section modulus is ph square over 4, like that. So if we draw the moment curvature relationship up to my, that is elastic, linear elastic. So curvature corresponding my is pi y, curvature at yielding, first yielding. And then from here to here, it gradually yield like that because top and bottom yield first as moment increase, right? So inelastic, gradual yielding. And then fully yielding case is MP. For rectangular section, MP is 1.5 mi, right? If you see here, over 6 over 4. Yeah. You already learned this content in your undergraduate course. But this is structural stability course, so we have additional P, axial force here. And we try to find moment, curvature, thrust, axial force relationship. Not only for moment curvature relationship, because we have axial force. Let's look at this. Yeah, this case, P is not 0 anymore. So we want to look at the moment, curvature, and thrust. Thrust means P. Thrust relationship. Okay, moment, curvature, thrust relationship. We have to derive that relationship from now on. For this case, let's look at the case 1. Fully elastic case. Let's look at this is the strain relationship, right? Strain is always straight, right? As you see here, at the centroid of the section, centroid of the mid-height of the section, we have the strain. Strain equal epsilon 0 because we have P. Due to this P, we have strain, average strain from here to here. And then you have the moment. So the moment calls the strain shape as the triangular like that. So fully elastic means the biggest strain among top and bottom is less than epsilon y. Okay, then it is a fully elastic. That means stress also less than sigma y, compressive stress and tensile stress. That is a fully elastic case. Let's look at the case 2, primary yielding case. Primary yielding means this top part yield. One side is yielded. We call it primary yielding. So if you see the strain relationship, that at the top, the strain is greater than epsilon y. At the bottom, strain is less than epsilon y. How about stress? Stress is that from this epsilon y, the stress is epsilon y. That is primary yielding case. Let's look at secondary yielding. Top and bottom, the strains are greater than epsilon y. Then is secondary yielding. This part is shows yield stress. This part also shows yield stress. That is case 3. Case 1, fully elastic. Case 2, primary yielding. Case 3, secondary yielding. You have 3 different cases. 3 different cases we can derive moment, curvature, thrust relationship. This elastic case, let's look at the geometry, kinematic. Epsilon equal epsilon 0. This is the strain at the centroid, plus this is curvature, and this is y, the distance from the centroid. Epsilon y equal epsilon 0 plus this angle curvature times y. then is epsilon y. From that geometry, you can get this equation. And then another one is material. Material is sigma equal E epsilon. Material means stress-strain relationship. Case 1 is elastic case. So stress equal E epsilon. Why? The stress is times E, elastic modulus times epsilon. That is the material relationship. Another term is that force equilibrium. So when we derive the equation, we usually use some geometry, material, and force relationship, kinematic, stress strain, and equilibrium equation to derive the equation. Let's look at the force. P equal integral sigma dA, right? Yeah, sigma stress and integral regarding the area. That is P, right? So integral h over 2 minus h over 2 dA equal p dy, right? P equal width dy. Okay, that this integral p dy means dA, right? Sigma equal E epsilon. Okay, that's the equation. Okay, your geometry epsilon equal this one. Okay, epsilon 0 plus curvature y. So you use the kinematic equation here. You use the material equation here, right? From this one, what is this? Integral E epsilon 0 p dy. What is that? E epsilon 0. They are independent from this integral, right? So E epsilon 0. And then integral b dy. What is that? Area A. Okay? E A epsilon 0. Then what happened this term? This term is disappeared. This term disappeared. What happened? Let's look at this is curvature. Curvature independent from this integral, right? So integral y b dy. What is that? The name is first moment of section. First moment of section. Regarding centroid. From y is distance from the centroid over section. What is that value? That value is 0. So this term is disappeared. So you have only EA epsilon 0. Let's look at the moment. Moment equal integral area sigma y dA. Sigma dA equal force, right? Times y. That makes moment. You input again the material relationship and then geometry relationship, then like that. Again, integral E epsilon 0 y b dy. That is first moment of section equal 0, right? And then integral E. E is independent, pi independent, okay, regarding the integral. So integral y square b dy. What is that? Moment of inertia, I. Yeah, so EI curvature. You have EI curvature like that. So if you use this m, small m equal moment divided by my. So let's call it is normalized m. M over mi equals small m. P over py equal rho. Okay? Now what is p? Your p equal E epsilon 0. E epsilon 0 means sigma. Sigma a. Py equals sigma y a. A deleted. So E epsilon 0 over sigma y equal rho. This small pi means curvature divided by yield curvature. Let's define like that. So we include small character m, small m, rho, and curvature. So as you see, the moment equal EI curvature, right? My moment equal EI yield curvature. So EI is deleted. The remaining one is curvature over yield curvature. That is identical to this small pi, right? So from this equation, we get the equation moment small m equal curvature. Small m equal pi. That is equation 1 for elastic range. In the same way, you can get equation for primary yielding. Yeah, that derivation a little complicated. You have that content in your textbook. The resulting equation of the relationship is that m. What is small m? Moment by my. Normalized moment, right? 1 minus rho. It is not p. Rho. This rho. Okay? normalized force. Minus E minus 1 minus rho, this rho also. Curvature is this one. This is not curvature, pi, small pi is normalized curvature. Do you understand? You have the equation like that too. Okay, case 3 is secondary yielding case. You can also derive the equation like that. You can refer to the textbook in detail. Yeah. If you use equation 1, 2, 3, you can draw the normalized moment, normalized curvature relationship from equation 1. M equal normalized curvature. Normalized moment equal normalized curvature. Okay, linear. Like that. And then primary yielding somehow here, secondary yielding somehow here. Like that. This one is your P equal 0 case. If P equal 0.5, then the curve looks like this. If P increase, the moment capacity decrease and decrease as P increase. So curve like this. So this one is called moment curvature thrust relationship. Of course, it is normalized form. This is structural stability course. You have one more term, thrust, P. Then let's look at this specific case, interaction curves of inelastic beam column. So from now on, we would like to derive interaction curves of inelastic beam column using the previous this equation. Interaction curve of inelastic beam column. There is interaction in strength of inelastic beam column. Interaction between axial force and moment. If axial force become large, then moment should be small for specific beam column. Okay? There are interaction. Let's derive that interaction curves of inelastic beam column. This column subjected to axial force, but the axial force has some eccentricity. So although there is no moment applied, but this axial force causes bending moment, okay, due to this PE, P times E. Let's consider the cross-section PH, rectangular cross-section. So let's assume this deformed shape as this sine curve. The delta at mid-length, the y at mid-length is delta. So y equals delta sine pi x over L. If you take derivative, then delta pi L cosine pi L x. Second derivative is minus delta pi L squared sine pi L x. Then let's look at the midspan curvature, pi m. This is pi m. This is in fact this pi equal large pi m like that. You have to modify like that. Large pi m. M means midspan. This is midspan. Let's consider curvature at midspan. Okay, that means this curvature is minus y2 prime. X equal L over 2 here. So here, if you input L over 2 instead of this x, then you can get delta pi of L square like that. Okay? From this relationship, you can get delta curvature m over typo. That should be pi over L square, right? Pi m. This is wrong. From this equation, you can get this one, pi over L, like that. And then let's look at the first order moment equal PE, right? That is the first order moment, P times E. So it is called M0 equal PE. M0 means first order moment. M sub M, that means moment at midspan, L over 2 here. Moment at midspan. Please don't confuse moment and midspan. So this moment and midspan mm equal m0, right? m0 equal p, right? Yeah. Times p times what? Delta, p delta. This moment equal pe plus p delta. p equal m0. So you can write this equation. And then let's normalize by my. m0 my equal small m0. 0 means first order moment. Small m means normalized by my. This one equal small m. Small m means normalized by mi. Sub m means regarding midspan moment. like that. If you rewrite this equation, small m0 plus p delta my mm. If you input this equation into here, let's calculate p delta over my. P delta over my. Delta can be write like this. my equal ei curvature y. Then ei L pi square. If you move this one into the denominator, that is PE. So this P. The remaining one is curvature M, curvature Y. So if you normalize by PY at that denominator, P over PY equal rho. PE over PY equal rho E. That normalized curvature, small pi. Small pi means normalized by pi y. Sub m means midspan. This equation m0, this one equal this one from this equation, and m. You get this equation. So normalize the first order moment can be written like this. If you move to this term to right hand side, that equation is 4. And then you have the equation 1, 2, 3 here. Already you have the equation. This equation 1, 2, 3. So this equation satisfied any point of the span. So now we are considering the midspan moment. This small m can be m sub m, right? Pi sub m, like that. From equation 1 to 3, we can let m equal m sub m, pi equal pi sub m, because this equation is satisfied any point in the span. So we are considering the midspan. So let m equal m sub m, curvature equal pi m. We can input 1, 2, 3 into equation 4. From equation 1 equal m equal pi m. Do you remember? M equal pi m. Okay. So if you input m equal pi m, then this equation can be pi m, this 1 minus rho e, like that. From the second equation, from your equation, this one, m equal pi m. Rho is regarding axial force. Axial force is always constant within the member. So we need not use rho m because it is constant along the member. Okay, so mm equal this equation pi m. If you input these two into equation number 4. So mm equal this equation, okay? From equation 2, pi m. K3, this equation, pi m, like that. Yeah, so you have the 3 equation, 5, 6, 7. From this 3 equation, you can draw this m0 and pi m relationship from this equation. If you draw this equation, then like that. You have some descending branch from here because the stability effect. If you do the stability analysis, you always have the descending part due to buckling, stability effect. If you provide the number B, H, L, E, sigma Y, and E, then you can draw this one. You know, these equations include this one, B, H, L, E, sigma Y, and E. Do you know where? Let's say rho equal P over PY. PY equals sigma Y and area, right? PH, like that. Do you understand? M0 is M0 MI. M0 equal PE, E included. Do you understand? Rho E means PE divided by PY, right? Let's say rho E equal PE divided by PY. PE is roller buckling load. L square, pi square, EI. This term include this L, E. So this term include these variables. Given value of these, then we can draw this curve. We can get the maximum M0. M0 is first order moment normalized by MI. If we apply different LR and E, LR is if you know L, if you know A and I, okay? When you calculate PE, there is I. So if you write again L, R. So L here. R equal square root 2 IA. Okay? You have A here. Right? I equal all over closed. L square pi square EI. Okay, it is include I already. So if you use the different LR E value, then you have different strengths. That means if you apply a different LR is slenderness ratio and E is eccentricity, then you have different strengths. If you have some small slenderness ratio, you have the large strengths, for example. If you have large E means large moment. That means you have small axial force can be obtained in terms of strengths. Okay, so you assign the different LRE. Then from this equation 5, 6, 7, you have this peak value, different LR and different E peak value. Then you can plot like that. Plot under some axis, normalize axial force and normalize first order moment. So you can plot this point, this point, this point, this point. For example, this point come from this point. So if you apply the different LR and E, there are many different points. This means different E. This one, this line, different LR. LR over 20, LR 60, LR 120, like that. Then you can get this curve. It is called interaction curve. It shows some strengths of beam column. Okay, interaction, axial force, and bending moment, considering inelastic effect already. So from this, the concept, the committee member developed LRFT interaction equation, the strengths of a beam column. I showed some the derivation and this figure for rectangular section for easily understanding the concept. But if the I-shaped section with residual stresses, it is impossible to derive this kind of equation. So we have to use numerical technique is necessary. Okay, everyone, see you next week. Bye bye.